Now on to section 3.3, and we'll deal with quadratic functions and their properties. The chapter deals with linear functions and quadratic functions. So here's the other side of the coin, having done the linear function stuff in section 3.1. Now, we're going to define and graph quadratic functions using transformations. You already know how to graph y equals x squared. It's in the library of functions. So we'll use transformations to graph more general quadratic functions than x squared. We'll define and identify the vertex and axis of symmetry of a quadratic function. These will be useful in graphing the function as well. We'll find a quadratic function from its vertex and one other point, and we'll find maximum and minimum values of a quadratic function. That's a big calculus puzzle, this last thing about maxes and mins. You'll leave Precalculus 1 with a little bit of ability to find extreme values of some very special functions, quadratic functions primarily. And that you will build on in Calculus 1. You'll have new techniques and you'll be able to find max and min values in general. You'll repeat this stuff and apply that technique to quadratic functions, probably as the first example, since these are relatively elementary functions. We'll also see the term parabola in here, formally defined, or formally associated, at least, with a quadratic function. I've informally done that in the past, but we'll get that term on the table in this section. So a quadratic function, by definition, is a function of the form f of x equals ax squared plus bx plus c, where a is non-zero. If a is 0, this term isn't here, and it's actually a linear function. So that's why that condition is there. Of course, the domain is all real numbers, no square roots, no division, so no concerns at this stage. A situation in which a quadratic function appears involves the motion of a projectile. Based on Newton's second law of motion, which says, in a nutshell, force equals mass times acceleration, it can be shown, ignoring air resistance, that the path of a projectile propelled upward at an inclination to the horizon is the graph of a quadratic function. You'll almost show this in Calculus 1, and I think you'll definitely show it in Calculus 3, and you'll likely show it in a sophomore physics class as well. So the idea is if you fire a projectile, then it's going to follow the graph of a quadratic function, as illustrated in figure 13 there. Let's do an example from the supplements. All right, let's look at number 24. I think I've modified it a bit from what the book states. With the instructions, graph the function f of x equals x minus 3 squared minus 5 by starting with the graph of y equals x squared and using transformations. By transformations, I mean shifting, compressing, stretching, maybe reflecting. So we'll start with simply the y equals x squared function from the library of functions. Here it is drawn in blue, and then we'll do things to it. Replace the x here with x minus 3 to produce an x minus 3 quantity squared. That results in a horizontal shift of the graph to the right by 3 units. Possibly go back and review that material on transformations. We have an x minus parameter. And when that parameter is positive, we shift to the right. But this statement comes with a minus sign. So x minus a, I think, was a parameter we used before. If we have x minus a, then when a is positive, the graph is shifted to the right by a units. Here we've got 3. So when we graph y equals x minus 3 squared, we get the blue y equals x squared shifted to the right 3 units to produce the green graph. Let's double check that. Let's see, 0 squared is 0. That's why the blue graph passes through the origin. When we plug in x equals 3 into the graph of y equals x minus 3 squared. Plug in x equals 3, we get 0 squared out, which is 0, of course. And in that sense, this point corresponds to that point. So there's more than just circumstantial evidence that, yeah, we should have shifted it to the right when we see the x minus 3. We're trying to produce x minus 3, quantity squared minus 5. Well, we just need to subtract 5 from this, from the green curve. Subtract 5 from the graph of this result, and that corresponds to a translation of 5 units down because we're subtracting 5. So the function f of x, as given, would result by taking the green graph and shifting it down 5 units. At some point in the past, the book has discussed key points. I'd call this lowest point, which we'll give a name to shortly. I'd call that a key point. And first, we had shifted that to the right by 3 units, and then shifted it down 5 units and carried all the other points along with it. So we've done the shifting. There's been no compressing and stretching, and there's been no reflection, so this one's a little bit easier to deal with. They start putting coefficients in front of some of this or in front of the x, then that makes it a touch more complicated. But in red is the graph of this function, and we got it by going to the library of functions and taking x squared and transforming it. And that's about the extent of the way we'll graph things in Precalculus 1. We'll add to the library a little bit later, but we'll still follow these same techniques. Returning to the notes, making an observation and introducing the term parabola. The graph of the quadratic function f of x equals ax squared plus bx plus c is called a parabola. So we'll just use that term. When you deal with conic sections in Precalculus 2, you'll give a more formal definition to what a parabola is. And you'll ultimately see that parabolas are the graph of quadratic functions. It opens up if a is positive, that is a is greater than 0. It opens down if a is less than 0, if a is negative. The lowest or highest point on the graph is called a vertex. Here we've got one opening upward. It must be the situation here on the left that a is positive. The leading coefficient is positive. We get open upward. Here's the vertex. It would be the lowest point on this parabola. Here the vertex is the highest point on the parabola. Here it must be that a is negative and the parabola opens downward. And we were calling this a key point in the previous example. It's the vertex, and it is a key point, but the vertex is this point, and certainly if we do transformations, following how that vertex moves in terms of shifts is certainly going to be an important way to determine the graph of the result. The vertical line passing through the vertex of the parabola is called the axis of symmetry. So the axis of symmetry, vertical line passing through the vertex. For us in quadratic functions, parabolas are always opening upwards or opening downwards. We couldn't have something maybe opening rightwards. Maybe take this and rotate it 90 degrees clockwise. Oh, that would violate the vertical line test. You may encounter this in other settings, but for us in the quadratic functions, these parabolas will always be opening upwards or downwards. In other settings, you might see them opening in different directions. And so the axis of symmetry will always be a vertical line for what we do. Okay, we're going to find a kind of a standard form of the equation of a parabola, I'd like to say. You'll deal with it like this when you cover conic sections, and that's verbiage you'll use. Here, we're just taking a quadratic function and manipulating it in a certain way. So consider f of x equals ax squared plus bx plus c. We're going to take that and do some completing of the square. First, let's take these first two terms and factor an a out. I got my reasons to be elaborated on here in the next line, but you'd agree I can factor an a out of those first two terms, and that'll leave us with x squared plus b over 8x. plus c. If you distribute the a back in, you'll get ax squared. The a's will cancel here, and we'll be left with a bx term, as we've got on the left-hand side. So that's certainly true. Why you would want to do that? Well, here's why you would want to do that. Now we're going to take this expression in parentheses and complete the square. To complete the square, see the appendix on polynomials. I think it's Appendix A3, where completing the square is dealt with. We need to take the coefficient of x, b over a, divide it by 2, and square it. That'll give us b over 2a, square that, b squared over 2a squared, or b squared over 4a squared. So we're going to add b squared over 4a squared because we're completing the square. Inside here, all right, we've actually added, since it's also multiplied by a, we've actually added a times b squared over 4a squared because we've done it inside the parentheses. So let's subtract a times b squared over 4a squared. Balancing the books, you know, we've really added and subtracted the same term, so we haven't changed anything. So it's algebraically equal as claimed, but this will be a perfect square. That's the reason we did that. This will be x plus the square root of this, b over 2a. X plus b over 2a is what we'll get. And then if you were to multiply this out, indeed, it would equal that. This is a technique of completing the square, and we've done it correctly. The b over a we had up here, we get b over 2a down here in terms of what we get when completing the square and then factoring. This stuff here, let's combine it. The denominator, well, if I cancel this a with the a squared down there, the denominator will be 4a. So let's get a common denominator. Let's multiply c by 4a over 4a, and that's what happens here and here. We'll get a common denominator and combine these two. Then we'll have 4ac minus, we're going to cancel that a, minus b squared. 4ac minus b squared all over 4a. So we could simplify this to the following. We could write this as f of x equals a times x minus h. We're going to take this as minus h. So we'd have to take h to be negative b over 2a. If you plug negative b over 2a in for h, we'll have x minus negative b over 2a, or in other words, x plus b over 2a. So we're simply introducing new variables to write the original equation in a different form. And then we'll call this thing here k. K equals 4ac minus b squared over 4a. All right. Then we can rewrite the original function, f of x equals ax squared plus bx plus c, as f of x equals a, x minus h, quantity squared plus k. Can't argue with the validity of it. All we really did was complete the square and introduce some new letters, h and k. Very suggestive of this h and k parameters. We use those for the center of a circle back in section 1.4. So they're playing a special role here as well. Here they are in terms of the a's and b's. So for that quadratic function, ax squared plus bx plus c, assuming a doesn't equal 0, or this isn't a quadratic function conversation, we're just dealing with a linear function, as this book calls them. The graph is a parabola with vertex hk. We found the value of h to be negative b over a, right, as given here. K, you can express k in terms of this, but it's going to be a point on the graph of the quadratic function. The less you have to remember, in my opinion, the better. If the x value is negative b over 2a, then the y value is f of that, f of negative b over 2a. So here's the h and k parameters. Indeed, if you'll plug negative b over 2a back into the original function, it'll produce this function value here. Alternatively, you could memorize this and say that's what we get for the y value. I'd say if you're going to do memorizing, memorize the x coordinate of the vertex. You can find the x coordinate of the vertex. You can use the function to find the y coordinate, and it's less stuff to remember. Negative b over 2a. That sounds so familiar. The quadratic equation contains something like this, the quadratic formula. Quadratic formula reads negative b plus or minus some stuff, all divided by 2a. Well, there's a negative b over 2a in the quadratic formula. There's some other stuff as well, the plus or minus square root stuff, but the fact that we get a negative b over 2a here and the quadratic formula also contains a negative b over 2a, that ain't a coincidence. We're very much close to dealing with the quadratic formula. I mean, we considered setting that polynomial ax squared plus bx plus c, setting that equal to 0. And the quadratic formula told you what the x values were. That involved a negative b over 2a, and so does this, and that's not a coincidence. So I think this should be easy to remember, because fingers crossed you remember the quadratic formula, because that's so fundamental to this class, especially when we do this second degree polynomial stuff. So the vertex is given by this as the claim, and the axis of symmetry is the vertical line x equals negative b over 2a. Yeah, that'd be the vertical line that passes through the vertex. Vertical lines are of the form x equals a constant, and the constant would be the point, or the x coordinate of the point that represents the vertex. So here we've got a formula for the axis of symmetry and a formula for the vertex, all in terms of A, B, and C. So what we've done is this again, but now in terms of A, B, and C, we have a formula for the vertical line. It's x equals negative b over 2a in both cases. And we have an equation that gives us the coordinates of this point. The x coordinates, negative b over 2a in both cases. The y coordinate is, well, it's f of that x coordinate. Let's think of it like that. We do have a formula for it. It also reminds me a bit of the quadratic formula, somewhat. But in terms of A, B, and C, we can find the vertex and the axis of symmetry. If A is positive, then the parabola opens up and the vertex is a minimum point. If A is negative, then the parabola opens down and the vertex is a maximum point, as in the previous picture. So this note, let's give it a name because we're probably going to refer to it, note 3.3.A. This tells us how to deal really with the graph in terms of A, B, and C. Given a quadratic function of the form f of A equals ax squared plus bx plus c, we can deal with the graph, that is the vertex and the axis of symmetry, in terms of the A's and the B's and the C's. Looks like the C's don't play a direct role in these two. Negative b over 2a plays the biggest role. C does play a role. It's somewhere inside this f of thing. Now, about intercepts, this we've basically done when we talked about the quadratic formula in one of the appendices. The x-intercepts of the quadratic function satisfy the following as a claim. If the discriminant b squared minus 4ac is positive, the graph of f of x equals ax squared plus bx plus c has two distinct x-intercepts, and so we'll cross the x-axis in two places. Discriminant, yeah, that's the thing of which we take the square root in the quadratic formula. So if that first case holds, make it a little smaller so we can see the picture and the statements at the same time. If the discriminant is positive, there'll be two places where the function takes on the value 0. So the picture looks something like this. This is a picture that's valid for A positive, right? Because it opens upwards. If it opens downward, we just maybe reflect this about the x-axis. But there will be two intercepts. There'll be two places where the function is 0, and the quadratic formula will give you the x values where the function takes on the value 0. It will give you both of those in the event that the discriminant is positive. If the discriminant's 0, there's only one point where the graph touches the x-axis, has one x-intercept, and it touches the x-axis at the vertex. Might look something like this. If A were negative, then we take this and reflect it about the x-axis. We'd have one opening downward that comes up and intersects and goes back down. In this case, we'd have one, if A were negative, that opens downward, comes up, intersects here, and then intersects there again. As I said, just take a reflection of this about the x-axis in the event that A is negative. But these are just diagrams, and they're pictures which reflect the behavior when A is positive. If the discriminant, b squared minus 4ac, is negative, then the quadratic equation is going to tell you there ain't any places where this function takes on the value 0. Well, there's not any real values for which the function equals 0. So it's either always positive or it's always negative. If it opens upward, it must look something like this. It has no x-intercept in this case. If A were negative, then it would be below the x-axis entirely and opening downward. So there, the claim is the three things that can happen in terms of intercepts. Let's go through and look at that real quick. It's not terribly surprising when we go through and appeal to the quadratic formula. We find an x-intercept by setting y equal to 0, or f of x equals to 0. Right? Y equals f of x is the plan here. So we'll set f of x, ax squared plus bx plus c, set that equal to 0. 3 little hash marks is kind of my way of saying set it equal to 0. But a quadratic formula will give you that x is negative b plus or minus square root of b squared minus 4ac divided by 2a. We're only considering real solutions, so we can't take square roots and negatives. If b squared minus 4ac is negative, this doesn't work. There's no real solutions, and that's case 3. So actually case 3 is the easiest one with which to dispatch. We'd get square roots and negatives. You can't do that. There are no x values satisfying this, and so there are no x-intercepts in the event that the discriminant is negative. Well, it'll still be all quadratic formula stuff in the next two cases. So let's do it again. If b squared minus 4ac equals 0, there's only one solution. Would be negative b plus or minus the square root of 0 divided by 2a. So all that plus or minus the square root of stuff, that's all 0. And we simply get negative b over 2a is the unique solution in that case of the formula f of x equals 0, y equals 0. So that gives us the unique intercept. If b squared minus 4ac is greater than 0, then the quadratic formula gives two solutions, negative b plus the square root of the discriminant over 2a, and negative b minus the discriminant, all divided by 2a. So as I said, it all just comes straight out of the quadratic formula in terms of this type of behavior. Returning to the notes. Okay, let's do a couple of illustrations. A couple of examples of this. Consider this function. F of x equals 4x squared minus 2x plus 1. Graph f by determining whether its graph opens up or down and finding its vertex, axis of symmetry, y-intercept, and x-intercepts, if any. Determine the domain and range of the function, determine where the function is increasing and where it's decreasing. Okay, this increasing, decreasing, and range stuff, we need the graph. So once we get the graph, the part B and part C stuff will be easy. Hard to find the range of a function unless you have a graph. If you got a graph, then it's no problem. So another reason to graph. All right, part A. They give us the function. ax squared plus bx plus c. So in that terminology, we have a is 4, b is -2, sign goes with it, and c is +1. So there's a, b, and c in this case. A is 4, 4 is positive, so the graph opens up. First off, they ask about that, so there's the answer to that part. Graph opens up. They wanted the vertex. Well, the vertex is -b divided by 2a and f of -b divided by 2a. Granted, we had a formula for that, but let's just use the function to figure it out. We've got specific numbers here. -b over 2a, let's see, b is -2 itself, a is 4, so -b divided by 2a will be -2 divided by 2 times 4. Careful with the parentheses there. Negative. So we get 2 divided by 2 times 4. Feel like the 2's cancel. And we get 1/4. So 1/4 is the x coordinate of the vertex. And the vertex itself is 1/4 comma, whatever the corresponding y value is. Let's just plug 1/4 into the function. Plugging 1/4 into function f gives us 4 times 1/4 squared, wherever you see an x, put a 1/4, minus 2 times x, minus 2 times 1/4, plus 1. I leave it to you to grind through that little bitty bit of arithmetic to come to the realization that the vertex is 1/4 comma 3/4. Simplify what's given there, and there's the vertex. They wanted opens up or down, vertex, we've done those two. Axis of symmetry, and some intercepts. Axis of symmetry is the vertical line that passes through the vertex. In general, it's x equals -b over 2a. We saw upstairs that -b over 2a is 1/4. So the axis of symmetry is x equals 1/4. We've got the vertex. It's the vertical line that passes through the vertex. So it'd have to be the vertical lines are of the form x equals a constant. It would have to be x equals 1/4. That's the x coordinate of the vertex. Y-intercepts. As we just saw in that theorem, that depends on the sign of the discriminant. The discriminant, b squared minus 4ac in general. In this case, b -2, a 4, c1. We'll plug those numbers in. -2 squared minus 4. That 4 times a is 4 as well. C is 1. Do the arithmetic. That gives us -12, which is negative. So we don't have any x-intercepts. The function is never 0. Alternatively, and this is where the theorem comes from, we could set the function equal to 0 and solve for x, as we've done in the past. We'd use the quadratic formula, and we'd get a square root of -12 in the process and see that there are no solutions to that. The theorem just gives us a shortcut on considering the discriminant. So no x-intercepts. For the y-intercept, we set x equal to 0, and that's straightforward because we have a function representation here. Setting x equal to 0, we get f of 0 is 4 times 0 squared minus 2 times 0 plus 1, as given down here. Of course, that's just 1. And so the y-intercept is 0. Okay, I think that took care of everything in part A except for the graph. So let's graph it on the next slide. Important stuff being 1/4, 3/4 is the vertex. It opens up. There's no x-intercepts, and there's a y-intercept of 1. Okay, 1/4, 3/4 will be the vertex. We'll start with that. So we'll go to 1/4, 3/4, my usual little image of graph paper here. There's the vertex, the lowest point. The y-intercept was 0, 1. There's the y-intercept. We know it opens upward. Well, how widely does it open upward? Does it open really widely or really narrowly? It looks fairly narrow. Let's plot a couple of other points. We do know it opens upward. Let's maybe plot what happens at -1 and +1, just to give us a couple of other points to get a cleaner graph. Plotting points in general is not a good way to graph. You know the story on that. We know this is the vertex and it opens upward, so we do know the shape of it. Let's get some more subtle details on the shape. If we plug -1 in, f of -1 is apparently 7. F of 1 is apparently 3. So that gives us 2 more points, -1, 7, and 1, 3. So here's 1, 3, here's -1, 7. That's the reason I want to plot those 2 points, as they fit on my graph paper. So maybe some trial and error to come to the realization that that's the 2 points I've got a chance of fitting on the page. And knowing the shape of the graph and a handful of points, the graph has to look a lot like that. So there's the graph. It uses the information we had. We could graph, if we were so driven, we could graph the axis of symmetry. It'd be the vertical line through the vertex. So it'd be the vertical line, x equals 1/4. But they didn't ask us to graph that. It's symmetric with respect to that axis, of course. And we've got the graph. In part B, they wanted to know about the domain. Well, I could have told you this to start with. The domain's all real numbers, -∞ to infinity. That's going to be the case for any quadratic function. Hey, you square stuff and you multiply and you add. Nothing can go wrong with that. So the domain will be all real numbers. Range, well, the range is easy now that we got the graph. I'm looking for y values. Doesn't take on these y values down here as I sweep back and forth. I don't touch the graph. I don't touch it till we get here to the vertex. And the vertex has a y coordinate of 3/4. The vertex was 1/4, 3/4. So 3/4 is the smallest value that the function takes on. And then it takes on all y values above that. So the range is 3/4 to infinity. Y is an element of 3/4 to infinity, if you like. So that's the y values associated with the graph. They wanted to ask us about increasing and decreasing. Okay, remember to read left to right, left to right. It goes downhill, apparently really, really steeply downhill, but it goes downhill till we reach the vertex, and then it changes to going uphill, apparently really, really steeply. But anyhow, it goes downhill, then uphill. It switches over at the vertex, which had x coordinate 1/4. So it's decreasing from -∞ to 1/4 and increasing from 1/4 to infinity. You want to include those 1/4 in terms of increasing and decreasing. Personally, I say you go right ahead. The book set it up where they only defined increasing and decreasing on open intervals. So that's why the book will express the answer like this. You'll deal with it somewhat differently in Calculus 1. And in Calculus 1, you'd actually include the endpoint of 1/4 in both of these. You wouldn't include the -∞, right? That's not even a number. That would be meaningless to try to include the -∞. It's not a number. This is a symbol for a interval that does not have a left-hand endpoint, for example, but it's got a right-hand endpoint, and we might include that in certain settings. Let's look at another one where they give us a picture, and then they ask us about the quadratic function that has this graph. So here's a graph. What's the quadratic function? They gave us the vertex. They've given us a y-intercept here. Looks like that's about all they've given us. We could find the axis of symmetry. It's the vertical line, x equals 2. X-intercepts, I can't really tell based on this graph. We must be able to find everything we need from the vertex and the y-intercept. All right. So suppose the quadratic function is of the form f of x equals ax squared plus bx plus c. Let's use these 2 pieces of information to see if we can figure everything out. We know the y-intercept. It's 0, -1. I just love 0. Let's plug that in. Take f of 0, because the arithmetic is so easy with 0, and we know what the function does at 0. Plug 0 in. Of course, we'll just get c out. When x is 0, y should be -1, so we must have c equals -1. Plug in 0, simplify, you know that must be -1, you conclude c is -1. So we need A, B, and C, and we got C. Other ways to approach this is written up in terms of discussing the axis of symmetry, could just as easily discuss the x coordinate of the vertex. It's the same information. The axis of symmetry is x equals -b/2a. We know the axis of symmetry is x equals 2, so we get this formula here. Equivalently, you could say the x coordinate of the vertex is 2, and the x coordinate of the vertex is -b/2a. So those things must be equal. So same information, just a different approach. This will allow us to get a relationship between a and b. Maybe multiply both sides by 2a, cross multiply. And we get -b is 4a, or maybe b equals -4a, multiplying both sides by a negative. And then we can express b in terms of a. So in terms of a, the function was ax squared plus bx, but we can replace the b with a -4a plus bx, but we're replacing the b with -4a, plus c, but we know c equals -1. So there you go. So this gives us the function in terms of a. We don't want it in terms of a, we want it in terms of numbers. What haven't we used? We've used both the x and y coordinate of this point, the y-intercept. This point, the only other piece of information we know, we've only used the x coordinate so far. We didn't use the y coordinate. This function, when I plug 2 into it, I get 3 out of it. We haven't used that value of 3 yet. You're probably going to need all the information they've given you. So I know the function is this form in terms of a, and I know when I plug 2 into it, we'll get 3 out. I know f of 2 equals 3 because the point 2, 3 is on the graph. So we must have f of 2, plug 2 in for x here. That'll give us a times 2 squared minus 4a times 2. Put the 2's in parentheses, as I'm prone to do when substituting into functions. Minus 1, that's 4a minus 8a minus 1. That's a -4a minus 1, and that should equal 3. We're setting that equal to 3. Arguably, I could put my 3 little lines there. We're setting it equal to 3 because we know f of 2 equals 3. Well, if that's the case, then we can solve for a, take the 1 to the other side, divide by -4. You'll find a is -1. And that was the missing piece. So f of x is of the form ax squared plus bx plus c. A is -1. B is, what was b? B equals -4a. Well, a is -1, so we'll plug that in there. So b is -4 times a times -1. It's +4. So b is +4. And we knew early on c was -1. So the function must be a -1 x squared plus b for x plus c minus 1. And there's the equation for the function that has this graph. So we've done this in both directions. We've gone from equations to graphs and from graphs to equations. Back to the notes. Final little observation. This is actually relevant information that's contained in what we've previously done. The quadratic function f of x equals ax squared plus bx plus c, where a is non-zero, is a parabola with this vertex, as we stated above. This vertex is the highest point on the graph if a is negative, and it's the lowest point on the graph if a is positive. Think in terms of opening upwards and opening downwards. If the vertex is the highest point, then f of that x value at the vertex is the maximum of the function. If it's the lowest point, then the corresponding y value is the minimum of the function. So we can find maxes and mins of quadratic functions by finding the vertex in terms of X value and Y value of the vertex, and then seeing if the graph opens up or opens down, giving us an absolute, if it opens up, an absolute minimum, if it opens down, an absolute maximum. Don't like bouncing around in the notes, but let's look at that first figure we had one more time. Opens up, it's going to be a minimum. Opens down, going to be a maximum. The highest point on the graph here, the lowest point on the graph here. So let's illustrate those ideas with another 4 examples. That'll take care of this section. Determine without graphing whether the quadratic function f of x equals 4x squared minus 8x plus 3 has a maximum or a minimum value, and then find the value. Okay, it's a quadratic function with a equals 4. 4 is positive. The graph opens up, must have an absolute minimum at its vertex. There's a lowest point on the graph because it opens upward. That is, there's an absolute minimum of the function. It occurs at the vertex. They ask us 2 things, max or min, first thing. Second thing, find the value of that max or min. So we need to find the vertex for this function, and we need to find the corresponding function value, corresponding y value. The vertex has x coordinate, negative b over 2a. Negative b over 2a, negative b over 2a. I ain't asking you to remember a whole bunch of stuff in this section, but you need to remember negative b over 2a, which sounds so familiar because it pops up in the quadratic equation, quadratic formula also. Negative b over 2a here, b is negative 8 and a is 4. So we'll have negative 8, there's b over 2a, there's the 4, and that reduces down to positive 1. So the vertex has x coordinate 1. By the way, the axis of symmetry is the vertical line, x equals 1, if you're into that kind of thing. They didn't ask us about that, but that's the case. To find the value of the function at the vertex, that is to find the y coordinate of the vertex, we just plug the x coordinate into the function. So we'll plug 1 into the function. That'll give us 4(1) squared minus 8 times 1 plus 3. 4(1) squared minus 8 times 1 plus 3, which must simplify to negative 1. And so we knew it had an absolute minimum, and now we know that absolute minimum is negative 1. When we dealt with extrema in the past, we looked at 2 things. What is the extrema and where is the extrema? Well, the where, it occurs at x equals 1. The what is the minimum? The minimum is negative 1. So we can accomplish all this stuff here really without a graph because we know opening upwards and opening downwards information, and we know where the max or min will occur. It'll occur at the vertex. So we just need to find the y coordinate of the vertex. Consider h of x equals negative x plus 1 squared plus 4. Graph h, determine the domain and range of h, determine where h is increasing and decreasing. All right, a little more complicated. This definitely is a quadratic function. We could multiply this stuff out, but you know, we had another way of dealing with quadratic functions in this form. Note 3.3.a, I called attention to it, said, if we have a quadratic function in the form a x minus h squared plus k, then the vertex occurs at the point hk. We went through and completed the square in that note and produced something of this form. We even had h in terms of the a's, b's, and c stuff. We had k, and I think in terms of the a's, b's, and c stuff. But when we have a quadratic function in this form, then it's easy to pick out the coordinates of the vertex. And we do have a quadratic function in this form. So we want to associate a, h, and k with the numbers up here. A Leading coefficient must be -3. By the way, that tells you something about opening down right there. X minus h is x plus 1. So we'd have to write this as x minus -1. And so h must be -1. Be careful with the negative signs. Pause the video and think about it. H must be -1. If we look at x minus -1, that'll certainly produce the x plus 1 quantity squared. K is easier, K is just 4. So we get A equals -3, H equals -1, and K equals 4. The vertex, as we saw in the note, occurs at HK. H is -1, K is 4. There's the vertex. Graph opens down, as we said, because A is negative. So that went by pretty fast because we took advantage of this form of the quadratic function. In Precalculus 2, you'll deal with parabolas, and you'll talk about probably the standard form of a parabola, and it'll look something like this. For now, we're just taking advantage of that form to pick off the coordinates of the vertex. The x-axis, the axis of symmetry is the vertical line through the vertex. So that would be x equals whatever coordinate we have, first coordinate for the vertex, -1. So x equals -1, that vertical line is the axis of symmetry. I guess they didn't ask us about that, but we're going to have to try to graph the thing. The y-intercept, let's find that. That's easy enough. You just plug in 0 for the y-intercept. Plugging in 0, we get -3 times 0 plus 1 squared plus 4. This would simplify to -3 plus 4, 4 minus 3. So this gives us 1. So the y-intercept is 1, x equals 0, y equals 1. And let's plot another point. Not -2, probably trial and error again. I plug in x values and find something that'll fit on my piece of graph paper. If we plug in -2 for x in the original function, it looks like we'll get 1 out, a small y value. So -2, 1 is another point on the graph. Trying to graph it, we know the vertex, -1, 4. We know the y-intercept, 0, 1. And we know the point -2, 1. Using that information and the fact that this is a quadratic function, we get something like this. So here's the point -1, 4. There's the vertex. Here's the y-intercept, 0, 1. There's the other point, -2, 1, the other point that we calculated. We know it opens downward, so it must look something like this. I really use these 2 points to go through and give me an idea of how to draw it, how wide it should be, how widely it's opening when it opens downward. Remember, we had an axis of symmetry of x equals -1. Hey, look at this. This is 1 unit to the right of that axis, and this is 1 unit to the left of that axis. So it's a symmetry that gives us that. Think you could find the x-intercepts? Yeah, well, I know I could. Looks like there's 2 of them. The geometry implies there has to be 2 x-intercepts. And we could go through with a quadratic formula and find the x values that makes the function 0. If you want that, not a problem. This is sufficient for a graph. Certainly there's details missing from it, but this will do for answering the question. It opens downward and it's shaped like a parabola. So it's like that. And that's in the right place. In terms of domains, of course, the domain is all real numbers. The range, see, this one has a maximum of 4 at -1. They didn't ask us exactly that, but that's the case. So this takes on no y values bigger than 4. It takes on 4 right there, and anything less than 4. Any y value less than 4, the function takes on. In fact, it takes them on twice. Once here and none above that. So the range would be anything less than or equal to 4. That is, in terms of an interval, the interval from -infinity to 4. Increasing and decreasing, they ask about in part C. Well, it's increasing up to x equals -1. and is decreasing after -1. The way we've dealt with it is in terms of open intervals. So here we would say f is increasing on the open interval from -infinity to -1 and decreasing on the interval from -1 to infinity. My next little speech is, okay, if this was calculus 1, you'd probably include that -1 in both of those intervals, which might seem a little weird that it would be both increasing and decreasing. A point that's in both of these intervals, but it's an endpoint and definitions are subtly different in calculus 1. For us, you leave the endpoints out. Let's do 2 more. All right, here they give you information. Find a quadratic function whose x-intercepts are -5 and 3 with first a equals 1, then a equals 2, then a equals -2, then a equals 5. They want to ask you, how does the value of a affect the intercepts? Part C, how does the value of a affect the axis of symmetry? Part C, how does the value of a affect the vertex? And finally, compare the x-coordinate of the vertex and the midpoint of the x-intercepts. What might you conclude? Well, first off, quadratic function, it has these 2 intercepts. All right, that tells you something about the form of the quadratic function. Since the x-intercepts are where the function equals 0, then with -5 and 3 as x-intercepts, we must have x minus -5, that is x plus 5, and x minus +3. These must be factors. The only way this function could equal 0 is if it has x plus 5 and x minus 3 as factors. So this function must be of the form a, leading coefficient, times x plus 5 times x minus 3. You would agree, I plug in -5, I plug -5 in, that'll make this 0 because it makes this factor 0. I plug in 3, that'll make this 0 because it makes this second factor 0. Rule of order, a can't be 0, you know, in the quadratic function setting, we wouldn't take a to be 0. So this must be the x-intercepts, -5 and 3. The thing I don't know what a is. We could FOIL this out and get a times x squared plus 2x minus 15. At this stage, I leave it to you to do the little details on the FOIL, but here's what we get by multiplying out. We could distribute the a, get ax squared plus 2ax minus 15a, having distributed. Let's call that function f sub a of x, and it depends on what a is, and they're going to change the value of a 4 times. They wanted to find the quadratic function for each of those values of a equals 1. Okay, we'll just plug 1 in for a, and we'll get, I'll call it f sub 1. F sub 1 is x squared plus 2x plus 15. Remember, we just took a equals 1, so easy arithmetic there. A equals 2, plug in 2, we'll get 2x squared plus 4x minus 30, as given down here, f sub 2. Plug -2 in for a, we'll get -2x squared minus 4x plus 30, as given here, f sub -2. A equals 5, plug in 5 for each of these, and it produces this function. For what it's worth, there's those functions of that form. Part B, how does the value of a affect the intercepts? If the x-intercepts are -5 and 3, then f is of this form. Changing a doesn't change the fact that this function is going to be 0 at -5, and this function is going to be 0 at +3. The a doesn't affect any of that. A has no effect on the x-intercepts. You set this equal to 0. Well, you set this equal to 0. I'd factor it and produce this. We could divide the a out. It's non-zero. That's part of the story. And then we'd see that either x plus 5 is 0 or x minus 3 is 0. And so that's the intercepts. So the x-intercepts are unaffected by a. Part C, they ask us about the axis of symmetry. Let's run back and look at the question again. How does the value of A affect the axis of symmetry? The axis of symmetry was the vertical line x equals negative b over 2a. For f of x equals ax squared plus 2ax minus 15a, the form of the function in terms of a, we have b, right? This is b in the ax squared plus bx plus c notation. So this is b, by the way, that's c, but we don't need that right now. B is 2a in terms of a, b equals 2a. So for any value of a, the axis of symmetry would be negative b divided by 2a. That would be negative, well, b equals 2a divided by 2a. 2a divided by 2a, just going to leave us with a -1, with the negative out front. So regardless of what a is, the a divides out here, as long as it's not 0. Regardless of what a is, we always get an axis of symmetry of -1. It's independent of this parameter a. How does a affect the axis of symmetry? It doesn't affect the axis of symmetry. The axis of symmetry is always -1, regardless of what a is. Just as in part B, the intercepts are always -5 and 3, regardless of what a is. Part D, let's look at the question again. How does the value of a affect the vertex? Okay, the vertex, that's a point, x comma y. The vertex has coordinates negative b over 2a and f of negative b over 2a. From part C, we see that negative b over 2a is -1. We just dealt with that. Negative b over 2a is -1. We had substituted in over here. So what's f of negative b over 2a? Well, negative b over 2a equals -1, so it's f of -1. We'll plug that into the function. Here's a convenient expression for the function at this stage. We'll plug -1 in for x. That'll produce a times -1 squared plus 2a times -1 minus 15a. Simplifying, that reduces to -16a. We've got, let's see, a minus 2a minus 15a, that'd be minus 17 plus 1, yeah, minus 16a. That's the y coordinate, the function value at the vertex. So the vertex is -1 comma -16a. For the first time, it's got an a in it. In these weird questions, they've asked us about how does a affect things. So as a increases, the y coordinate of the vertex increases, or sorry, decreases because of the negative sign. A is a bigger and bigger positive number. -16a is a bigger and bigger negative number. So there's one way to express it. But definitely a does affect the y coordinate of the vertex. So I've got no expressions of a in the axis of symmetry, no a's in the intercepts. They're always -5 or 3, follows from these two factors, but an explicit appearance of a in the y coordinate of the vertex. So however you wish to express it, definitely the vertex is affected by the value of a. It affects the function values and so affects the location of the vertex. Let's read that part E again, because that was a little weird. Part E says, compare the x coordinate of the vertex with the midpoint of the x-intercepts. What might you conclude? Okay. The x coordinate of the vertex is -1. Right, there's the vertex right there. The x coordinate's -1. We had the intercepts, the x-intercepts were -5 and 3. We had that from the given information. They wanted the midpoint of the intercepts, so we just add those together and divide by 2. We get -1 as the midpoint of those two intercepts. -1 comma 0, if you want to express it as a point. Hey, they're the same. The midpoint of the intercepts is the same as the x-coordinate of the vertex. Well, that makes pretty good sense. Think geometrically of what's going on here. X equals -1. It's the x-coordinate of the vertex. As a line, as a vertical line, it's the axis of symmetry. Well, how far is it from -1 to 3? 4 units to the right. How far is it from -1 to -5? 4 units to the left. So -5 is the same distance from -1, the axis of symmetry, as 3 is from -1. So that makes perfect sense that the midpoint of the intercepts would be the axis of symmetry. And the axis of symmetry is going to be, as a vertical line, x equals -1, that'll be the x-coordinate of the vertex. So this ain't a coincidence. What will happen in general is the x-coordinate of the vertex and the midpoint of the x-intercepts, they'll be equal. Not all of these have x-intercepts, but when they do have 2 x-intercepts, then the midpoint of those 2 x-intercepts will be the vertex, the x-coordinate of the vertex. In general, they're equal, assuming there are 2 x-intercepts. And finally, some kind of like real world data. So we might have to do some numerical approximations on this. This happens with the uglier numbers. In the United States, the birth rate, capital B, of unmarried women, births per 1,000 unmarried women, so units for B, for women whose age is A, is modeled by the function B of A equals -0.30 A squared plus 16.26 A minus 158.90. What's the age of unmarried women with the highest birth rate? Part A. Part B, what's the highest birth rate of unmarried women? Part C, evaluate and interpret B of 40. Okay, so regardless of all the words, they're asking us birth rate. Maximize birth rate. Birth rate is given by this function. They want the maximum value of this function. Remember, this is all about quadratic functions. So they just pick some words to produce a problem that involves quadratic functions. How realistic it is, I don't know. But the leading coefficient's negative. So this would be an opening downward parabola. And in fact, the vertex would represent the highest point on that parabola. So that's how we'll find the A that gives the highest birth rate. The value of the function will give that highest birth rate. What we're doing is we're finding in part A, if you will, the x-coordinate of the vertex, and in part B, we're finding the y-coordinate of the vertex. And then in part C, we're just dealing with a function in terms of what it represents. First, function B is a quadratic function. They're using A as a variable, which is not terribly convenient because we've used A to represent something else, and we've almost always used X as the variable, but that's part of the fun of the real world. The coefficient of the square of the variable is -0.30. Like this thing here, it's negative. So that tells you the graph of B opens down and B has an absolute maximum at the vertex. So let's find that vertex. You know the vertex is at the point, say A, B of A. So be the coordinates of the vertex symbolically. All right, this is where them using A becomes quite a challenge here. We had this as, in our terminology, it was -B divided by 2A. Apologies. A is playing the role of the variable here. So what we would have is negative the coefficient of the variable, -B, divided by 2 times the leading coefficient. So we'll have negative this divided by 2 times that. If we had used X for the variable, this would be A, -0.30. This would be B, 16.26. By the way, that would be C. With that in mind, we get negative 16.26, the thing playing the role of B, divided by 2, thing playing the role of A, 2 times the leading coefficient, negative 0.30. Do the arithmetic there, and it comes out as 27.1. So the age of unmarried women with the highest birth rate is 27.1 years, according to this model. There's where the maximum occurs. Part B says, what is the highest birth rate? That is, what's the maximum of the function? A is negative. We know we have a maximum. We know what occurs here. So all we got to do is plug this in to the function for A. That is, we need to compute B of 27.1, plug 27.1 in for A. It produces 61.423. The units were what? Births per 1,000 unmarried women. So 61.24 is the corresponding function value in appropriate units. So it's just a question about finding where the maximum is, part A, and what the maximum is, part B. In part C, they want us to evaluate and interpret B of 40. Okay, we'll plug 40 into the function. Here's the function. Replacing A with 40 produces 11.5 births per 1,000 unmarried women. Interpret this. Well, of 1,000 unmarried women of age 40 in the United States, remember it's a rate, 11.5 will give birth in an average year. So that's the meaning of this particular little model. The models are more interesting in this section than they were in section 3.1. In 3.1, we just had linear models. So these models, realistic or not, especially in this last one, these models are a little more interesting. They have maxes and mins because you know their graphs are either opening upwards or opening downwards parabolas. We, in Precalculus 1, we can find those maxes and mins. Just find the vertex. Since we're dealing with quadratic functions, that's the way to go. In terms of more complicated functions, in Precalculus 1, we don't have a way of finding maxes and mins. That's one of the most useful things you'll do in Calculus 1. You'll use Calculus 1 to graph functions. You'll be able to determine where a function is increasing and decreasing. So we're foreshadowing that, talking increasing and decreasing in the graphs we are given. And you'll be able to find, using that increasing, decreasing information, where the maxes and the mins are. And we're foreshadowing that as well in pretty limited cases because we can't really graph a whole lot of stuff. We can graph the stuff that's in the library of functions, and that's about it in Precalculus 1. In Precalculus 2, you'll take on trig functions. You'll actually be really good at graphing trig functions. You'll re-encounter trig functions mixed in with other functions in Calculus 1. But one of the main applications of Calculus 1 is to graphing, and hence to find an increasing, decreasing information, and finding maximums and minimums. So Precalculus, we're doing what we can, foreshadowing what you'll see in Calculus 1. Thank you for your attention. I'll see you in the next section here shortly. Have a nice day.